So question 1, spectral fast Fourier transform analysis is to be used to study the response to a rectangular pulse of 0.01 seconds in duration. A resolution of 10 Hertz is required of the spectrum. Give an estimate for the minimum data acquisitions or sampling rate and the number of data points required. Okay, so to work out the period, the frequency of these pulses, okay, rectangular pulse of 0.01 seconds, obviously the input frequency is 1 over the period, and the period of that pulse is 0.01. So 1 over 0.01 gives us 100 Hertz. 100 cycles per second. So we know that the sampling rate, okay, Fs, needs to be at least twice times by the input to avoid aliasing. But we're also using, so it's got to be at least 200 Hertz. But because it's a fast Fourier transform, FFT, means that this needs to be 2 to the power of something. And so above 200 Hertz, the next one up is 256. So there's our sampling frequency. And so to calculate the number of samples, so the number of samples, you take your sampling frequency, Fs, divided by your resolution, which was given in the question as 10. So that means you've got to take 26 samples. Obviously, you can't have half a sample. It's either got one or it hasn't. So that's why 256 divided by 10 gives 25.6. So that means it's got to have at least 26 samples. Nice and easy. So again, this is a very similar problem. It says if a Fourier spectrum of a signal up to 1 kilohertz is required to give a frequency resolution of 5 hertz, estimate the minimum number of points that need to be sampled. Okay, so again, Fin is 1000 hertz. Therefore, Fs needs to be greater than 2000 hertz. Okay, in this case, we don't know whether it's a FFT or not, so the number of samples is 2000 divided by 5, so we get 400 samples. And if this was an FFT thing, then obviously this would be, yes?
Why is it over 10?
Because in the question it says a resolution of 10 hertz is required. So if this was an FFT, then this would obviously, this number here would be 2048, because that's the next one up from 2000, that's 2 to the power of something. Then the next question says if a signal is of 400 hertz is sampled at 95 hertz, what is the aliasing frequency? So we can, this is where that n, the problem of n comes in. Fn is 400 hertz. The Fs is 95. What's Fa? Well, Fa equals the absolute value of Fin minus NFS. Okay. Now, what does n need to be for 95 to be, 95 multiplied by n equals 400? Well, the closest value of n is going to be 4. And so we've got 400 minus 4 times 95. And so we end up getting 20 hertz. So with question 3, if you had a frequency of 400 hertz, your input frequency, let's say you had a sinusoid, okay, and you sampled it at only 95 hertz, if you tried to go back to the analog signal from the digital points that you got, you might end up with a frequency of only 20 hertz, when in fact it was 400. Okay, so that's what's going on. And then it says, what is the alias frequency when the sampling is increased to 100 Hertz? Well, here it's the same problem, but FA is Fin minus N Fs. Again, N is 4 in this case. 400 minus 4 times 100, we end up with 0 Hertz. So that means that if your input signal was a sinusoid of 400 Hertz, you're measuring at 100 Hertz, you might end up with a solid line in your, as your, you know, if you went backwards. Okay. You can imagine if your input is a sinusoid, and that's 400 Hertz. You're measuring at 100 Hertz, you'd be picking up this point, 1, 2, 3, this point, 1, 2, 3, and so on, and you'd end up with a solid line. Oops. Okay. Let's move all that up. So here's your sinusoid signal at 400 Hertz. At 100 Hertz, that's going to be 4 times slower. And so you pick up this point, say, and this point, and if this continued on, yeah, 1, 2, 3, this point. And if you drew them all in a line, you'd end up with no frequency whatsoever. It wouldn't oscillate whatsoever. Okay.